Good morning, everybody. This is the one-dimensional collisions video. I'm going to work through an inelastic one-dimensional collision, and then I'm going to go through an elastic one-dimensional collision. We're going to start with inelastic, and I'm actually going to pull one of your homework problems for this, or at least half of it, and that's the railroad car collision problem. Now, for you guys, that is problem 9. For us, it's going to be problem 34 because I'm doing the version in the book. Now, I don't think there's any significant difference between the two, but just a heads up. So, I'm going to read this problem out, then we'll talk about it a little bit, and then we'll get started. I'm only doing part A of that problem because part B gets more into momentum energy interactions, which is not something that we're quite ready to deal with yet. So, just part A. All right. A railroad car of mass M, so M1 equals M, moving at a speed V1, okay, so that would be V1 equals V1, I guess. Collides and couples with two railroad cars, each of the same mass M and moving in the same direction at a speed V2. So M2, the second collection of railroad cars, is M plus M, because there's two of them stuck together. And then the velocity of that is going to be V2. There's no numbers in this problem, if you haven't noticed that yet. Determine VF of the three coupled cars after the collision in terms of V1 and V2. What that means is they want us to write an equation to find VF if we had M, V1, and V2. So that's what we're going to do. We're going to try and substitute this in and calculate what VF should be. So VF is what we're trying to find. Now, normally this will be a little simpler, so I want to lay out a couple of things real quick. This is going to be object 1, and this is object 2, where we have the first car that's moving along with mass M and traveling at velocity V1, keep making an I. And it encounters two carts that are coupled. That's a little short. Both of these have the same mass as this cart, but they're traveling at a slightly slower V2. So this is initial. Final, what happens is this car collides with these and then couples with them. So now we have three cars all linked together and all traveling together with some velocity VF. And that's going to be our final. So then what the law of conservation of energy tells us, which the law of conservation of energy is how we solve all collision problems, whether they be one-dimensional or two-dimensional. What the law of conservation, did I say energy? I mean momentum. If I said energy, I meant momentum. The law of conservation of momentum is what we use to solve these problems. What that tells us is that the total momentum initially has to be equal to the total momentum finally. So this momentum plus this momentum has to be equal to this momentum. So we can write that as an equation. So the momentum of the first object, which would be m times v1, plus the momentum of the second object, which would be 2m, or m plus m, which would be 2m, times v2, so 2m times v2, is equal to, this is initial, is equal to our final momentum, in which all three of them are stuck together. So that's going to be 3m times the final velocity, vf. And this is the final. Well, right off the bat, something that jumps out at you. M is present in all three equations, so we don't actually need m in order to solve this. So it becomes v1 plus 2v2 equals 3vf. So to actually solve that, we're just trying to get vf by itself. We just need to divide by 3. So our final equation would be, make sure I'm not in the shot here, would be v1 plus 2v2 divided by 3 equals vf. Now, in this case, that's the end of the problem, because they didn't actually give us any numbers to plug in here to find vf. So all we have to do is just calculate the equation that we would use. So that's the end of this one. Normally, you would then say, okay, well, I know what v1 is, I know what v2 is, let's calculate vf. But that's as far as we're going to be able to go in this problem without numbers. So that is a basic one-dimensional collision in which both objects are traveling in the same direction. Okay, now that is an inelastic collision. The next one we're going to do is an elastic collision. So I'm going to step off the screen. You guys can pause this, go back, take a look at some things, and then I'm going to start this back up here in a bit. I'm going to pause it, erase the board, and then we'll start in on problem 43. So, all right. So same thing on this one. The second half of the problem really gets into momentum-energy interaction, so we're only going to do part A of this. But this is an elastic collision instead of an inelastic collision. So I'm going to read this out and put some information on the board. All right, a 5-gram object moving to the right. So I'm going to call that object 1. So 5 grams. That's a mass. That mass, though, is in grams and needs to be in kilograms. So I'm going to convert that to kilograms here in a bit. So M1 is 5 grams. And it is traveling to the right at 20 centimeters per second. So right is going to be that way. So I'm going to call that positive. So we have V1 is positive 20 centimeters per second. So that's our object 1 information. Makes an elastic head-on collision with a 10-gram object that is initially at rest. So M2 is 10 grams, and its velocity is 0 meters per second. Yeah, so this is going to be our initial velocity for both of these. Okay, because this is before the collision happens. This mass is traveling at this velocity, and this mass is sitting still. So that's before the collision. So those are our initial values. Okay, find the velocity of each object after the collision. So that's what we're going to be working on. So we are looking for VF, or V1F and V2F. So I'm going to draw out a diagram and we'll get started on this. Okay, so I saw a potential problem here and I went through and ran some numbers and I was right. We can't actually solve this without doing the energy portion of this. So I'm just going to walk you through writing out the elastic collision equation, the momentum equation, and show you why we have to use energy to actually solve this. But we're not actually going to find an answer. I want to show you how to write out the equation, though, so you've got another example. So we're going to start off with the objects initially. We'll draw a diagram of finally. Excuse me. And then we'll write out our equation. But we're not actually going to solve this one because, again, momentum energy stuff is not something I think we're ready to get into yet. So I am going to assume that because they don't really tell us anything about these objects, I'm going to assume that they are billiard balls because that makes this easier to draw for me. So that's what I'm going to do. So we have object 1, object 2. Both of these are the initial position. So we have object 1, which is traveling to the right with a velocity v1 and a mass m1. And then we have object 2, which is sitting still, so v2 equals 0. So it's not moving anywhere, and it has mass m2. These two collide, and what happens? Well, part of the issue here is we don't know for sure what direction v1, or what direction the first mass is going to be going in. Will it hit and continue in the same direction, or will it hit and rebound? This is why you're not going to see a lot of elastic collisions in this chapter. Elastic collisions are a lot harder calculations to work with. Most of what we're going to be dealing with is inelastic collisions. Now, most likely, considering that this one is not moving, this should either stop moving or continue in the same direction, but at a lower velocity. So we're going to assume that it continues moving in that direction. But at this point, V2 is probably going to have a higher velocity than V1 does. So now we have M1 moving at a, oh, I forgot the I's on these, at V1 final, and M2, I keep drawing smaller and smaller circles. Hang on. At V1 final, and M2 is also traveling in the same direction at V2 final. Now, the equation then is going to say, since neither of these are traveling at the same velocity, this is initial and this is final. We have two separate entities both times. So when we write out our conservation of momentum equation, hold that thought. Sorry about that. When we write out our conservation of momentum equation, we have to treat each of these as a separate entity. So let's start with V1, an initial. So we're going to have initial equals final, just like we did before. So M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Now, this is 0 because this object is not moving. Since its velocity is 0, its momentum has to be 0. Now, if M1 and M2 were the same or very nearly the same, then what would most likely happen is that the velocities would swap. But because M2 is significantly larger than M1, they can't just swap their velocities. So that makes this calculation just a little bit more difficult. It means that both of them are going to be moving still after the collision. So at this point, we know this, we know this. I should switch colors for this part. We know M1, we know V1I, we know M1, and we know M2. But we do not know V1 final or V2 final. You can't solve one equation with two unknowns, so we have to write a second equation. That's where the law of conservation of energy comes in, because since this is an elastic collision, energy is conserved. So we can use the total initial energy and the total final energy to calculate what one of these, or to find basically the same thing. That gives us two equations with two unknowns, and then we can sub out one of our velocities. But this is as far as we can get without diving into energy, which is not something I think you guys are ready for just yet. So here's the promise that I'm going to make. When we do matter-energy interactions, I'll come back and finish this problem for you guys. And I'll show you how to finish this one out. So that's it for this video. It's getting a little longer than I wanted, so I'm going to go ahead and stop it here. Hope y'all are having a wonderful day, and I will see y'all later.